We're going to do partial fractions today and tomorrow. And then Friday, we'll be able to do tables. We might even use Party Friday to do partial fractions. Well, before we even go near the process of integrating fractions, which is essentially what 7.4 is about, how do you integrate a fraction, we're going to have to pick up some skill building. So let's look at special integrals. In particular, we're going to look at integrals of fractions. And these particular guys I'm going to show you are to make your life a bit easier, right? They're kind of shortcuts, things that if you remember them, they make your life a lot simpler. So let's start with a guy that you should know. Isn't he one of our standard integrals? Sometimes I write it as x squared plus 1, you know it's the same thing, right? What is that guy? What's the antiderivative of that fella?
Tangent inverse.
Yeah. Technically plus c, right? We know that guy, but you know that I'm going to write it this way, I guess because my brain likes it that way. We can actually integrate a whole family of questions that look very similar. This last one's a general version of that. So I'm going to tell you the answer, and then you're going to look at it, and hopefully you're going to say, I think I know the trick here. The antiderivative of this guy is 1/2 the inverse tan of x over 2. The antiderivative or integral of this guy is 1/5 the inverse tan of x over 5. Anybody want to have a shot at what the third one is based on the pattern that hopefully you've seen in the first two?
One-tenth.
Yeah. And what goes here?
X over 10.
So if you ever need to find the integral of 1 over x squared plus 100, can't you just remember it? Yeah, like you remember what that guy is. So in general then, 1 over a, the inverse tan of x over a plus c. So you could add that. I haven't got many of them, but couldn't you add it to, you know, the kind of list of things we just know because we've got a good memory? Right. So there's a new guy to our list. Next fella. This special integral. We know this guy, don't we? What's the integral of 1 over x?
ln x.
Right. Now we're going to use them. To allow us to find integrals of any linear function, any linear fraction, right? This guy here, right? This one is 1/2 the natural log of 2x plus 1. This one is 1/3 the natural log of 3x take away 4. This fella, want to have a guess at what he would be? This fella.
Negative 1/5 the natural log of 4 minus 5x.
Yeah. In general, 1 over ax plus b, where a can be any number you like and b can be any number you like. The general version of that is 1 over a, the natural log of ax plus b, add c. Now, you know that's essentially the linear shortcut method, isn't it? But just for one specific situation. So think about this guy here as a shortcut for being able to write the answer to any of these integrals by just writing down the answer. You don't need to do any u subs. Actually, if you wanted to do all these questions from scratch, wouldn't they all just be a u sub? For instance, wouldn't this be the u sub 2x plus 1? This would be the u sub 3x minus 4. And this would be the u sub 4 minus 5x. And it would work, and you would eventually get the right answer. But isn't it better if you can just short circuit the whole thing and just say, oh, I've got a little shortcut for that particular situation? Are we okay with those two special integrals that we can now add things that look like this and just write down the answer right away, or things that look like this and write down its integral right away? I'm a great believer. If it saves time, isn't it worth it? If it makes your life a little bit easier, a little bit less working, it's worth it. So now we're coming to number 2. Not so nice. We're going to look at a technique called long division. Long division allows us to take a polynomial divided, in this case, by x plus 2, and rewrite it in terms of what's called a quotient, which is essentially like a whole number bit plus a remainder. You learn how to do this in 141, and it took place a bit in the middle, I would guess, and you probably did it for 1 day. So it's not a thing that you've used a lot, and you probably have vague recollection of it. Do you have a vague recollection of long division? But not a lot of practice at it, right? So we are going to have to do, I think it's in 2 questions, you're going to have to do some long division, 2 or 3, that's it. So, but for the 2 or 3 questions that you need it, you need to know how to do it, right? It's one of those kind of, there are not a lot of questions that do it, but you need to know it because of those questions. So here is the process. Now you may have been taught a different way. I hope not. But if you were taught a different way, then you're going to have to figure out how to do it using the way you were taught. This is how I would do it. You set it up basically like this. And then you go through a kind of process where you keep repeating the process till you're done. So what does that process look like? Cover up everybody except the 5x cubed. Cover up everybody except the biggest term, in this case, x. And then you look at what you need to multiply x by to get 5x cubed. Okay, so what do you need to multiply x by to get 5x cubed?
5x squared.
Then what you do is you take 5x squared and you multiply it by these 2 terms. So you get 5x cubed and you get 10x squared. I like to put a big bracket around it and subtract. That's basically to remind me that I'm going to subtract all of this red stuff from the black stuff. So 5x cubed, subtract 5x cubed, gone. 2x squared, subtract 10x squared, negative 8x squared. Negative 3x take away nothing, and negative 7 take away nothing. Are you comfortable with the process? That's one turn of the handle, right? That's the process that you turn the handle.
Could you
And then-
explain?
Mhm.
Sorry. Could you explain that last part? How you got the 8x squared?
2x squared subtract 10x squared leaves negative x squared.
Okay.
So when I put these brackets and that minus, that's to kind of force me to recognize that I'm subtracting everything. It's very easy not to do it if you don't emphasize it. Okay, then we start again. Cover that guy up, cover that guy up. And now we ask ourselves, what do you need to multiply x by to get negative 8x squared? So what do you multiply that by? Agreed. And then you go negative 8x times this, negative 8x squared. Negative 8 times this is negative 16x. Big bracket round it, subtract. And let's go. Negative 8x squared, subtract negative 8. Isn't that adding 8 so they kill each other off? Bit messier the next one. Negative 3x, subtract negative 16x. That is negative 3x add 13x. That ends up being positive 10x, and then that guy's there. So negative 3x, subtract negative, I can't count. When the heck did that come from?
You just did 13 twice in your head.
There. Negative 3, subtract that. That is positive 13, which is much better than it was the time before. Negative 3, add 16, 13. One more time. What do you multiply x by to get 13x? And the answer is 13. 13 times x, oh, get my color scheme all wonky, is 13x. 13 times 2 is positive 26. And subtract. 13x, take away 13x, gone. Negative 7, take away 26. I hope that's negative 33. And that is long division in all its glory. So what does that tell me? It tells me that I can rewrite this fraction in terms of two pieces. One piece is called the quotient, which is this guy. My scanning. 5x squared minus 8x plus 13. And a remainder. And the remainder is written as a fraction. So this piece is called the quotient. And this little piece here is called the remainder. Do you have memories of doing this now? It's called long division. It allows you to take any polynomial divided, in this case by a linear term, and convert it into this. Well, you might think, what would be the benefit of that? Well, how about if I wanted to integrate this? Wouldn't this be impossible to do with any of the techniques that we have? Can you trust me? There's not that a U sub in the world is not going to save this. It's definitely not integration by parts, and that's about it. We don't have any other techniques, right? But won't it become this guy's integral? Well, don't I know how to integrate all these guys? And is it not just a log? So this guy would become x cubed, so 5/3. This guy would be minus 4x squared. This 13 would be 13x. And this guy would be negative 33 log x plus 2. So what it allows us to do, this long division technique, is it allows us to integrate certain fractions. Are we good with that one?
Is this also called synthetic division in this? I'm not
It's called synthetic division when you write it down in a slightly different form. Synthetic division looks like that with a number here and some other guys, and the remainders there, and you get some things. So it's the same process, but it uses a different technique. So if you've heard of synthetic division, you're in the right ballpark. Sometimes when you do this question, there might not be an x squared, right? It might just be 5x cubed minus 3x, right? That can happen. If there isn't an x squared there, some people put 0x squared, just so that they can keep things vertically matched. And some people just leave a big gap for the same reason. Do you want another long division? Or should we continue to the last step?
I'm good with continuing.
Nobody else got a strong opinion otherwise? Okay. I guess you'll find out whether you need more practice when you hit your first question in the homework, right? So hopefully that'll be good. Okay, now partial fraction method. Well, we're going to look at a skill here. And the skill that we're going to look at is how you take a general fraction and break it down into little baby fractions called partial fractions, and what the structure of those guys look like. So I'll give you an example of what's going on. The typical question that you're going to ask to do partial fractions with will look like this. Some polynomial on the top, unfactored typically, and some guys on the bottom that should be factored. And if they're not, then you factor them, right? You're expected to do it, right? Now, they are going to be broken into two fractions. Would that seem reasonable? You would break it into two fractions. And one of the fractions is going to be that guy, and the other fraction is going to be that guy. Would that seem reasonable that this single fraction could be broken into two separate fractions? And the reason why this works is we can then integrate these two separately and get the answer. And these guys here are what are called the partial fractions, right? These fellas here, they're called partial fractions. And later today, I'm going to show you how to actually get the terms that go here. But right now, I just want to focus on the structure of what these look like. Whenever you break this up, this fraction will have a single number above it, and we'll call that a. On the other hand, the quadratic always has two terms, and we'll call them bx plus c. So in this method, we are eventually going to find out what the numbers for a, b, and c are. But we have to know that they are three numbers to find, right? Only one here, but two here. Okay. How about suppose I wanted to split this into partial fractions. How many would we use? Agreed, 3. 1 for each fraction, right? Now, since these are linear terms, won't that mean that they're just a missing number? Not an ax plus b, but just a missing a missing b, and a missing c. So you notice the slight difference between how this partial fraction gets split and this one. Let's try this combination. So this is me just building up another skill. How many partial fractions would this guy be split into?
2.
Great. And would you agree that the first one would probably be this guy and the other one would be that guy, right? What's missing on the top, an A or an AX plus B?
BX plus C.
Or if you want to go those letters. Right? And won't this one be? We'll call it CX plus C. Every one gets its own letter because every one will probably be a different value. Now I've done every permutation except one. And it's the weirdest one. Let's just change the top. This one looks a little bit weird. So let me just tell you what you get. It's going to be a number over x minus 4 plus a number over x minus 4 squared. That's good because I can integrate that. That's going to be a log. And I can integrate that. Trust me, that's just going to be a power rule. So anything you like, right? 5x plus 10 on the top, x minus 4. Do you see that that splits as two pieces? So I think I've covered all the permutations of what the partial fractions would look like in any given starting fraction situation. You think you got them, the partial fraction piece of the puzzle in your head now? So let's do one. Let's take 4x plus 1 over x plus 1, x minus 3. And let's do a partial fraction. Well, I need to split it into its two partial fractions. This is kind of cool, but it is magic, as you're about to find out, I hope. Right. Would you agree the two fractions are x plus 1 and x minus 3? And that is essentially step 1. You're going to be given that guy is going to be integrated, but let's just forget about the integration right now and just do the partial fractions. Now, the next few lines are all leading towards one thing. I want to know what A and B are. I want to know what numbers they are, because they are going to be numbers. It'd be great if they were 4 and 3, yeah, nice numbers. But they're probably going to be 3/17 and -7/17 because they just tend to come out ugly. So don't let the fact that A and B end up being really messy, yucky kind of fractions. Most of them are, right? It's just the way the numbers work. So how's this magic going to work? Well, I've taken this fraction and I've said, I can break it into two partial fractions. I'm now going to take those two partial fractions and I'm going to stick them back together. Now, the only way that you can add two fractions that don't share a common denominator is, don't you have to give them a common denominator? And the way I do that is by multiplying by a special version of 1. And since these are now a shared common denominator, won't it just be this guy plus this guy? Which almost looks cyclic. Hey, you broke it apart, so why are you sticking them back together again? And when you stuck them back together again, they're even uglier than they were when they were separated. But nonetheless, You always do that. And then we use a piece of logic. If two fractions are equal to each other and their denominators are the same thing, then you are allowed to make the assumption that aren't the tops equal to each other, which I'm now going to call step 3. So far, so good. Now, this is the guy that is pretty much the bread and butter of this process. Now we have this step. Now, before we talk about what I'm going to ask you here, this line says mathematically that 4x plus 1 is equal to this for every single value of x. If I plug in 42 for x and I plug it in here, they're both going to equal each other. If I plug in 7 each time, they're both equal. Yes?
Wasn't b x plus 1?
It was. Thank you. Okay. So, pick any x you like, not a good idea. Pick a very special version of x and nice things will happen. Can you think of a value of x that's going to make it so that I can figure out A or B? Choose an x that makes
Zero.
it easy.
3 or -1.
Okay, let's pick 3 then, which is a good choice. Now, if you pick 3, won't that be 4 lots of 3? Won't that be 13? And here's the cool part. What happens if you pick 3 for x? What does this become? 0, which means doesn't that disappear from the problem? And if you plug it in here, what you have then is basically 0 b times 4. So that makes 13 4b, which makes b 13 quarters. And you've now discovered one of your 2 missing answers. Time to choose another x. I think you already mentioned what that could be, but could someone else have a look and see if they can come up with the same number?
-4.
Well, it would be if that was a 4, but since I changed it to a 1, it'll be -1.
-1.
Yeah, well, that was me, not you. Okay, now, wait a minute. I know what b is. So I'm going to rewrite the information. Like that. Now, I could have left it as b, but if you know what it is, shouldn't you call it what it is? It's 13 quarters. Right? Okay, what's going to happen when you plug -1 in? Well, 4 lots of that, that's -3. Put in -1 there, you're going to get -4, but won't that become 0? And so that makes a 3 quarters. So we now know that the original fraction is equal to a over x plus 1 and a b over x minus 3. Now suppose you wanted to integrate this, then don't you just integrate the partial fractions? Okay, isn't that the log of x plus 1? And so 3 quarters, the natural log of x plus 1. And isn't this going to get you the natural log of x minus 3? So you have 13 quarters, the natural log of x minus 3, and then add a c, and you are done. So what we've now got is a process that allows us to find the integrals of weird fractions. Kinda cool? Let's do one more because that's all we have time for. While I'm getting set up for the last question, you want to say hi? Okay, let's imagine we're being asked to find the integral of this guy. So we'll start with x squared plus 2 over x minus 3 over x squared plus 4. And we'll do the partial fraction thing, right? Hopefully you would be able to identify that that's the two partial fractions, right? Okay. Do we need one piece or two pieces above an x minus 3? Is it going to be an a on its own or an ax plus b, I guess? What should be here?
Just A, right?
Yeah. And what about above the x squared plus 4?
BX plus C.
Good. Are we comfortable with that process? That's kind of your step one. You kind of need that, don't you? Right. Now, in step 2, I'm now going to have to put the fraction back together again. So that means this guy gets multiplied by this fella, and this second one, doesn't he get multiplied by the x minus 3 fella, right? So we now have x squared plus 2, this guy, is the same thing as a lots of this guy plus bx add c of this guy all over x take away 3 x squared plus 4, right? That would be my step 2. So partial fractions get combined back together again. We've got this. What does the next line of working look like?
The denominators cancel.
Correct. And I'm going to go and start a new piece of paper. We've got to pick an x, but we have to be quite careful about choices of x's, right? Because every question is a little bit different from the previous one. There is one value of x you should choose first. Even if you can think of a couple of ones that might work for other reasons, there's only one value of x that's going to be the correct first choice.
3.
Explain why. It's correct. What's the benefit of choosing 3?
Sorry, my computer is iffy. I can't always press the button. It's the only way you can for sure get one of those terms, A, B, or C, canceled. And it cancels out the B and the C because you're multiplying them by 0.
That makes sense, guys, why that's the right choice. When we do the choice of x's, don't we only want one letter left alive? I don't care if it's A, a B, or a C. That doesn't matter. But I want one letter, whatever it is. And can you see why the choice of 3 works really well for this question? So 3 squared is 9. 9 plus 2 gets me 11. A times 3 squared, which is what? 9 plus 4. Add a whole load of nothings, so I won't write it down. That gets me 11 equals 13a, and that gets me a is now 13/11. Are we cool with that? I now know
Not
what
the
A
way
is.
you wrote it. You
Shouldn't it
left
be
off the 1.
1113?
Thank you.
Right. Are we now good with that? Right. I'm now going to go over here and update the information. And it's important that you do that, because if you don't, you may not be able to figure out who the next X is. Because there's only 2 guys missing now, right? There's only a B and a C missing. I've already replaced A by what it's worth. Okay, time to think. I need an X.
Do we distribute that A and then subtract both of those to the other side so we can figure out what X is going to cancel out?
I wouldn't choose to do that, Kathy. I'm not saying that might
I
work,
do.
but picking an X is going to make it much easier. Just picking the right X is the problem. Arwen, did you have an idea of an X to choose?
Could we do 0 to take out the bx so we can get C?
That's exactly what you do. Does that make sense now? You see why X equals 0 is going to kill that. And remember our goal. I only want 1 letter left alive. Right? So B, making X 0, essentially for a little while, right, kills off that fella. So let's see what we now have. We have 0 squared plus 2, which is 2. I have 11 thirds, 0 squared plus 4, plus 0 in C just gets you C, and 0 take away 3 gets you -3. So 2 equals, yikes, 44 thirds, take away 3C.
Isn't it 13ths?
What happened there? I keep losing my ones. Right. God, it's probably even uglier than it was. Now, tell me what to do in the next line. Don't let the ugly fractions make you change your mind. Do what you would have done if it was nice numbers.
Subtract 44/13 from both sides.
Right, and the only reason I'm writing this down is to make sure I don't screw up. Well, that's what, 26/13 take away 44/13. You know this is all done by calculator, right? What does that get me? 4 gets me, I make it -18/13. And then divide everybody by -3 and you get +6/13. So actually nicer than it might have been. Don't we now know what C is? It's 6/13. And I'll go over here and I'll now update my information. 11/13 x squared plus 4 plus bx plus 6/13 x take away 3. Oh, we still have one last unknown guy to get. And we still have to choose an X. And I think, I don't know why, but I think sometimes that's the hardest one. And actually, it should be the easiest one. I might think, well, what do you mean? How could that be the easiest? I mean, just look at how ugly that is. How could picking an X be easy? But it is.
Why not just pick one?
Yeah, why don't you just pick any random X you like? I think 1's a good choice because it's small, right? But couldn't I pick 42 and it would still work? Trust me, it does. Pick 89 if you feel like picking a weird value of X. Every single value of X that you choose will eventually give you the same B at the end. So I think the problem might be when you've got an infinite number of choices, people find it difficult to make a decision. There are, of course, two guys you can't pick. You can't pick 0 or 3 anymore. Would you agree those two have been used up and can't be chosen again? But with the exception of those two guys, anybody really would work. So I'm going to choose 1 because I think it's a good number. 1 squared plus 2 is 3. 11 thirds, 1 squared, that's 5. Plus b times 1 is b, plus 6/13 times -2. (55 thirds), -2b, negative.
I think that's 55/13.
Yeah. And 12/13. I guess I should combine these a little bit. Is that 43/13? Okay, take it away from both sides, although that would probably be something I should do in a calculator, but to heck with it. On the paper, might as well just keep going. Looks like it's what, -4/13. And that gives you eventually +2/13. So haven't we actually found A, B, and C? I won't have time to do the integral part, but at least I can set up what the answer would look like. Here is our original fraction. It was going to be A over x minus 3 plus bx plus c over x squared plus 4. But we got A is 11/13. B is 2/13. And C is 6/13. Then there's one other thing that we should do, and that is if you have a quadratic term at the end, split them. Now, can you imagine there was an integral around this guy? Won't that guy just be a log? Won't that guy at the end? Okay, not the nicest thing in the world here, but isn't that a half inverse tan of x over 2? And a half with that is where that comes from. And then I've got this awkward guy in the middle. How will I find the integral of that guy? I need a method, a technique. So I can't just write the answer down like the other two. Do you
Drop
recognize?
your 13 again.
Might as well just be consistent and drop it all the time. Right, back to that question. What should you do to solve that? Suppose it was 2x over x squared plus 4. What would you do to solve that?
A U sub.
Yeah. Is the fact that it's 2/13 x throwing you a little bit? It's a U sub. A U sub of x squared plus 4. With some really darn ugly fraction in the top, but all of them have got darn ugly fractions, so we just have to live with that. And that's essentially what we'll be spending tomorrow doing. Integrating functions using partial fractions. Any questions before we call it a day? What's the difference between snakes and politicians?
Snakes don't lie.
No. Some people like snakes. No? That's all I got for you. Okay, guys, have a nice day. Bye-bye. Someday, I believe, might be staying behind because I have, oh, Ali, I like that joke. For a homework, if you want to stay behind because you have a homework question, feel free to do so.
Thank you.
You're welcome. You got a homework question, Sam?
Yes, I am pulling up.
Okay.
Right now.
Javon, you get one as well? I'll just put you on mute. As soon as you've found it, you can tell me. But there was a lot of background sound, that's why I put you on mute.
Okay, so should I share my screen?
Sure, I'll give you the permission. Oh, no, I've just shared my screen. That's not what I wanted to do. I wanted to let you share a screen, which is different. Okay, you should have the ability to share now.
Okay, can you see this?
I'm assuming it's question 5.
Yes.
Okay, I'll just take a note of that and then we'll work on it.
And I have-
right, hold on, just a quick thought here. I'm going to go and get the answer to that one because I think I might know what's going on. But just in case I won't, I'll write down the question and we can figure it out. I'm wondering if it's WebAssign having problems with tan inverse 1 and whether it really wants it to be called arctan of 1. Because tan inverse 1 could be confused by it as a tangent to the power of -1.
Okay.
You see what I'm getting at?
Yeah.
So if I check the answer and it just says arctan 1, then you haven't made any mistakes at all, right? So
Okay.
I need you to, I'm going to have to steal permission so I can go back to my own screen and find what that question looks like. It's question 9. It's from trig substitution, right?
I thought it was question 5. Yeah, question 5.
Question 5. Okay, question 5. And oh, that's interesting. That doesn't have an A in it. I'm looking at the wrong one. Now it has an A in it. Right. What was your answer again? I should have wrote that down as well. Did you have an inverse tan of 1?
Yes.
What is the value for the inverse tan of 1?
Some decimal.
No, it's not. Although it could be a decimal. It does have an exact value. Oh, no, it doesn't. Take that back. I'm thinking, no, I am. Inverse tan of 1 is pi over 4.
Oh, that makes sense. Pi. Yeah, that's it. Okay.
Did that fix it?
So what this should be is instead of the inverse tan of 1, it should just be pi over 4.
Yeah, and then tidy it up.
Okay. So
According to the answer I'm looking at front of me, there isn't any pi's. So that must mean there must be a pi somewhere else that's going to cancel with it.
Huh. I don't.
So you don't see that.
No, I don't see where we would have, where it would have canceled.
Oh, did you return back to the x's?
Yes.
Then you shouldn't have any inverse tans if you return back to the x's, should you?
Okay, so how do I, how would I convert inverse tan to x?
Well, no, you won't. It's before that. You had an answer with thetas and sine thetas in it, didn't you? Did you?
Yes, I'm looking at my, for my notes right here. So before that, yes, I did.
So all those guys get turned into x's.
Mhm.
Oh, did you pick up an inverse tan in there somewhere?
So when determining theta, I brought in an inverse tan.
Okay, Len, we need to go and do that question from scratch because that doesn't match what the answer is telling me here. So I need to go through it and you can just look at your working and if there's a mistake, we'll figure it out, right? That has to go away. I have to go back and share with this fella. Okay. You have a 9 here, right?
Yes, I do.
Yeah. Can I just ignore the 9 and just remember there's a 9 times at the end? Saves
Yes.
me having to write it all over the place. Right, so what was the U sub going to be? A tan theta, agreed?
Yes.
And so when you differentiate that with respect to theta, a tangent gets you a secant squared, so an A tangent gets you A secant squared theta. And that gives you du is A secant squared theta d theta. You agree with that?
Yes. Do you mean dx?
Dx. Yes.
Okay.
So we have got an integral of a secant squared theta d theta all over an a squared, which is what a squared plus an a squared tan squared theta, all raised to the power of 3/2. Do we get a guy that looks like that?
Yes.
That guy's good to go for a little while. Won't this guy in the bottom get you an a squared secant squared?
Yes.
And raised to the 3 power 3, the third power, you get that guy.
Yes.
And there's a cube in there as well, right? So far, so good. That gets me 1 over a squared and a 1 over secant and a d theta. Do you get that?
So let me look. Okay, so I got, that's where I made the mistake. I did secant squared. I only
Okay,
took,
and then you went a tan road, and that's probably where that came from. This fella, of course, is much better like that. Your right angle triangle then is going to be x over a, which makes this guy the a squared plus x squared, which is fine, makes this guy theta. It does mean that the cosine of this guy, right, well, first I've got to integrate it before I get too ahead of myself. Right. And the sine is x over the square root of a squared plus x squared, evaluated at 0 and evaluated at a. And then hopefully off you go.
Okay. Yeah, that makes sense. I don't know where I was going with the rest of this. That'll take some looking at, but.
Well,
yeah,
if this step's wrong, it won't matter what you did. You might have done the correct answer if that had been secant squared, but it's not. So that changes the whole ballpark.
Yep.
Okay,
Okay.
we get anything else, or are we good?
I would like to go over at least one more.
Sure. What you got?
Me real quick. So how about number 8?
Number 8. Let's see what my 8 looks like. My 8 has a square root of x squared take away 25 over an x cubed. What's your guy got?
Mine is the square root of x squared minus 4 over x cubed.
Okay, so we'll use that one. This one has a plus c on it. Yeah, okay. Who's the u sub for this question?
I'm looking for my notes right now. Squared minus 4, that's it. The u sub I used was 2 secant theta.
So du, then I go with u subs, it's x, right? So dx by d theta is going to be 2 secant tans. And that makes dx 2 secant tan d theta.
Mhm.
So we're cool with that. Okay. Square root of 4 secant squared theta take away 4. X cubed becomes 8 secant cubed thetas. And dx is 2 secant tans d theta. Does that look right?
Yes, it does.
So you recognize that guy is 4 tan squared on the top.
Yes.
So that becomes 2
Oh.
tan theta times a 2 secant theta tan theta d theta all over an 8 secant cube theta. 2 and 2 gets you 2. 1 secant gets you a secant squared. So I'm left with tan squared theta over 2 secant squared theta. That doesn't look good.
Yeah, so I did something wrong with the looks like
Oh, I know where to go. Oh, so you never got to here.
no, I didn't.
Right.
I
Okay.
see where I got it wrong though.
Okay. I know where to go with this guy, but so let me take it just one step further. So if when you get to it, you can finish it. Can you see a way of tackling this guy? Because a U sub doesn't work, which is what worried me.
Yeah. So
So what might I do instead?
secant squared being brought up as cosine, and that cancels it out to
Right.
1/2 sine squared.
Right. We get yes. And then can't we do the sine squared as a half, 1 plus 1 minus the cosine of 2 theta, and then, you know, do your thing.
Huh, that's weird. I got to there too.
Oh, so let's keep going.
Interesting.
It's a half, 1 minus the cosine of 2 theta, d theta. Did we do that?
Yes.
Which, let's take that quarter out. It's a pain in the butt anyway, right? Got that guy?
Yes.
So that's going to get me a theta negative 1/2 the sine of 2 theta. Are you happy about the negative 1/2 sine 2 theta back?
Yes.
So I have got 1/4 theta, 1/8 sine of 2 theta.
Yep. And at that point, I had converted sine of 2 theta to
2 sine theta, cosine theta.
yes.
Yeah, so that would be a good idea. That does reduce your thing to a quarter now, doesn't it?
Mhm.
And then it's build triangle.
Yep.
Well, in this case, x over 2 is a secant, which is another way of saying 2 over x is a cosine.
Mhm.
So opposite adjacent hypotenuse, 2 over x gets you the square root of x squared minus 4, which is exactly what we want, isn't it?
Yes.
And so you just put all the pieces together and it should come out.
So, yeah, so I got all the way up to there. So,
Well, okay, I guess we should keep going then, because there's not much left to
Yeah.
kind of go astray. So let's see what we have. Won't theta, well, you can write theta in 2 different ways. If you use this thing, won't theta be the inverse secant of x over 2? But if you use this version, won't theta be the inverse cosine of 2 over x? They're both equivalent.
I used the inverse cosine of 2 over x.
Okay, so 1/4 inverse cosine of 2 over x. Take away 1/4. The sine is that over that. And the cosine is that over that. So I have 1/4 inverse cosine of 2 over x. Take away 1/2 the square root of x squared minus 4 over x squared.